So I think that we had got as far as, well, having come back to the question of the Schwarzschild metric. The Schwarzschild metric is of this form, and we'd studied what happens if you introduced a retarded time coordinate u. Of course, if you stare at this metric, it's invariant under time reversal, and this, of course, has picked out one particular direction of time. You could, of course, send t to minus t, but it's more convenient to introduce a retarded time coordinate, t plus r plus 2m times logarithm of r minus 2m, and end up with the metric ds squared is equal to minus into 1 minus 2m over r dv squared plus 2 dv dr plus r squared d omega 2 squared. Can someone show me exactly where we got to on the previous thing? Not the...
Just drawing diagram.
So we've drawn that diagram. Do I need to redraw that diagram? Well, it wouldn't hurt. So we had drawn a picture of the VR plane, which looked something like this. R was going off in this direction. R equals 2m is here. And lines of constant v were going to be lying in this direction. And the null lines that represent outgoing null geodesics would look something like this. There's something wrong with my picture. So what happened was that light cones look like this in this region. The outgoing null geodesics look something like this, so that the light cones were tipping over, pointing inwards as you get here. And then over in this region, you are forced to move inwards. So this surface r equals 2m is the boundary of a region that cannot be probed from outside. So this too is a horizon. This, however, is a black hole horizon because you cannot see into it, hence black. If you are sitting out here, then there are no light rays from this surface which can reach you. For that reason it's called a black hole. I always find this diagram a bit confusing. Penrose diagrams are really rather more straightforward. And if we draw a Penrose diagram of what happens in the v, r, theta, phi coordinates, then it will look something like this. Again, there will be the same asymptotic region that you had before. So this region here is the same as what happened with the u, r, theta, phi coordinates. Here is space like infinity. future and past time-like infinity. And it's basically the same picture that we had before, except upside down. That's hardly surprising because this thing is invariant under time reversal. So we should expect everything to be invariant under time reversal. So if you construct the Penrose diagram, we don't really know what's going on there, but we do know that there is something singular happening here. So we have some picture that looks like that. This is the surface R equals 0, of course, where the curvature blows up. If I draw lines of constant t and constant r in this region, again, you can see that well, lines of constant r will look something like this. So it's exactly similar to what happened before. And as you go to r equals 2m, you find yourself on this surface. If r is tending to 2m and v is finite, this thing is going to minus infinity. So if v is finite, t is going to plus infinity. So the essential difference is that the Schwarzschild time coordinate t is going to plus infinity here, whereas in our previous construction with ur theta phi is going to minus infinity down here. So if you drew lines of constant t on this picture, which we can do in a different colour, they will look something like this, and they will be going to plus infinity as you move up towards the horizon, something like that. So these are constant t. Finally, if I draw lines of constant advanced time v, then those will just simply be straight lines. They are null curves in this picture, and they go like this. So this encompasses the fact that you cannot see inside this region. If you think about what astronomers do, they sit at large distances from any interesting place safely. That's usually at Scry, somewhere up here. They look along their past light cone. That's something which looks like this. And even if they move up in this direction, of course, they will never see into the region behind the horizon. And that's the basic point about black holes. There are regions of space-time which you cannot probe from the outside. So a black hole in general is bounded by a horizon. And you cannot probe its interior from the outside. Now, if you think about it, a trial definition of what is meant by a black hole horizon would be it is the boundary of the causal past of Scry plus. If you think about it, here is Scry plus, so you're interested in the past light cone of everything at Scry plus. That is everything which is to the past of this surface. So it's all of this region here. And this is sometimes called H plus to distinguish it from a surface that you get in the UR theta phi coordinates. Now you can see that there is something profoundly alarming about this picture. Of course, I can't probe this region from the outside, but there's nothing stopping me falling in. I could choose to be in the outside region and move to here and say I'm going to probe the inside by that method. But now you can see that this is terrible. It's terrible because once you are here, you've still got to move in a time-like direction, so you are forced to move in the interior of your light cone. something like that. Light cone's going to look like that always. So if you have found yourself in this region and you move along any time-like line, you are forced to meet the singularity. So all time-like curves inside the horizon will reach the singularity. Furthermore, that will happen in a finite amount of proper time according to your clocks. We will probably see that later when we do some explicit calculations. So, at least in the language of classical general relativity, you will, if you pass through here, you will get to here and fall off the edge of space-time. Nobody knows what that means. There is a lot of discussion as to what it means, but I am not able to tell you the resolution of that problem. You might argue that the fact that this happens is a consequence of the incredibly large symmetry that we had here. We said that everything was absolutely spherically symmetric. That turns out to be untrue. The singularity theorems of Hawking and Penrose, which I might discuss briefly, prove that whenever you have a horizon, there is always some kind of singularity associated with it. So the surprising thing is that this singularity is not a consequence of making assumptions about symmetry. So that, crudely speaking, is what happens, what a black hole is in relativistic theory. However, we've obviously done something quite wrong here. You see, we have managed to find an extent coordinates VR theta phi, which enlarge the space-time from this original region where TR theta phi works, and we discovered a region up here. We found a set of coordinates in which UR theta phi worked, and found another region down here. And if I try to draw that on this picture, it would look something like this. So it is obvious that something is missing, because I could, for example, start at this point in space-time, and whilst I could end up here, there's nothing stopping me going in that direction, and I don't know what happens. So it's obvious that something is missing. So we need to work just a little bit harder to see what is going on. Now, the obvious thing to do, I imagine, is to say, well, getting rid of t and having UR theta phi worked, or having VR theta phi, that worked. So the next thing that you might try is to have u and v and theta and phi. Maybe that gets you somewhere interesting. So that means you get rid of r as well as t. Now, a moment's thought will reveal that that is going to cause a certain amount of difficulty, because if I look at the difference between v and u, half of v minus u is equal to r plus 2m times logarithm of the modulus of r minus 2m. A half of v plus u is t. So there isn't any problem with this, but if I just tell you v and u, finding r can be a kind of complicated. So the solution to that problem is to say, well, of course, these two equations implicitly determine r for you. If I tell you what v and u is, you can tell me what r is, but you won't be able to solve that equation analytically. Too bad. So, in v, u, theta, phi coordinates, you can calculate the line element and you will get ds squared is equal to minus into 1 minus 2m over r du dv plus, make absolutely certain that I have not left something out. And that's it. Plus r squared d omega 2 squared. So this is obviously a brave try, but this metric is completely degenerate at r equals 2m. So that corresponds to v minus, well, you can see that you're obviously asking for trouble because this thing is infinite. So if you think about this thing as a matrix, it's not invertible at r equals 2m. Its determinant vanishes. You can determine r everywhere from u and v except at r equals 2m. So you know that something peculiar is going on, but the fact that this thing vanishes, even as a function of u and v, tells you you're in big trouble. For this reason, curiously, Einstein thought that the Schwarzschild solution made no sense whatsoever. And it wasn't until 1958, somewhat amazingly, that someone figured out how to get rid of these coordinate singularities. The coordinate singularity at r equals 2m here can be eliminated by a technique of Kruskal and independently Szekeres. They were space-like separated from each other, one being in the United States and the other being in Hungary. So it really is independent. They said, well, you just exponentiate little u and little v. So they invented a set of coordinates which unfortunately usually goes by the name of Kruskal coordinates, although I think really Szekeres did it first, often the way. Big V is e to the little v over 4m, and big U is e to the minus u over 4m with a minus sign. This works only in the exterior region, r greater than 2m, a region which I will call region 1 in this slightly complicated diagram here. So in this region, I have deliberately chosen u to be negative and v to be positive. If I look at the line element in these coordinates, the easiest thing to do is just to simply work out what happens when you differentiate these things. D big V times d big U is minus e to the v minus u over 4m.
Is region 1 the diamond shape? Or is it?
Region 1 is bounded by this line here and this line here. Sorry. This diagram will get repeated shortly, so don't worry too much about that. d big V, d big U is minus e to the v minus u over 4m, a 1 over 16 m squared times dv minus du. And if you think about that, this is equal to, from the definition of little v and little u, minus e to the v minus u over 4m, 1 over 16 m squared. And then from here you will end up with a 2 into, wait a minute, I mean dv times du. I don't know why I said dv minus du. And if you think about that, that is the same thing. I got no simplification between there and there, so get rid of that. So d big V, big U is the same thing as minus 1 over 16m squared, d little u, d little v, and then this factor here just gives you a minus uv again. So it's u, v, plus sign. If you substitute that in, you will discover that you will end up with ds squared is equal to 16m squared over r, e to the minus r over 2m, d big U, d big V, plus r squared into d theta squared, plus sine squared theta d phi squared. Now, of course, when I do that, you can go back to the r, t, and r coordinates in region 1, just from the definition in terms of little v and little u. So it's kind of easy. The product uv is the same thing as minus e to the v minus u over 4m. That's the same thing as minus e to the t plus r plus 2m times logarithm of the modulus of r minus 2m twice divided by 4m, so that's over 2m. So that's the same thing as minus e to the r over 2m, and then a factor of r minus 2m. Similarly, if you calculate u over v is minus e to the minus t over 2m. Now we can try to redraw this diagram. So region 1, we decided, corresponded to where u was negative and v was positive.
I'm sorry, because of the logarithm, they can change type. They can change signs, no? U and V.
Big U and big V?
Oh, no, the small u and small.
The small u and small v, the point is that little u is well defined in region 1 and well defined down here, but we don't know what it does up there. Little v works fine in this region, and we worked out what happened up here. And the fact that you say that there is a potential problem with signs reflects the fact that what we have done is not complete. So the whole point is to introduce big U and big V coordinates to get around that problem. You knew that you had to do that because this metric here is singular.
What I mean is it's not always the same sign in region 1. It can change signs, which is not what you wrote.
Little v, you say that little v runs from minus infinity to plus infinity as we go from there to there. So if r goes to infinity, then you end up with that. Yeah, that's right.
it said that it had only one sign.
Little v?
Yeah.
I don't think I said anything about little v. I said something about big V, not little v. Big V has only got one sign, and you can see that. You see, this thing I defined to be a plus. V goes from minus infinity to plus infinity, and then V is positive. So these relationships work in region 1. Now, if I've done this right, U equals 0 on this surface. You may remember that we said that if t went to plus infinity, you found yourself on the horizon up here. I hope that that's come out to be true. If u goes to plus infinity, this is e to the minus infinity, which is 0, and whatever the sign of little u is, big U is negative, so I seem to have got it right. This surface here corresponds to big U equals 0. Similarly, if you calculate what happens to big V, you will discover it's 0 on this surface. Yeah, that's the right way around. That's because little v is going to minus infinity on that surface. E to the minus infinity is 0, and you get there from above because v is positive. So we do seem to have managed to do it right here. If you stare at this form of the metric, nothing peculiar happens at big U or big V is equal to 0, and it's absolutely fine. If you needed to calculate R, you would go back to this formula. So I can use this under all circumstances, and if I decide to be just a little bit more relaxed about what I mean by T and R, and decide that what I really meant was the modulus of U over V is the modulus of E to the minus T over 2m, and the modulus of UV was equal to the modulus of E to the R over 2m. Then I can construct values of T and R for all values of U and V. So you can sort of see what happens now. Here U was negative and V was positive. U is 0 here. So in this region, the interior of the black hole, I can arrange for U to be positive and V to be positive. In the past, on the other side of this boundary where V is equal to 0, V is negative and U is negative. And then you have the singularity running here. Now, there is nothing peculiar about big U or big V being equal to 0. So this surface, big V is equal to 0, can be just simply continued. There's nothing to stop me continuing it. And so I'll end up with a picture that looks like that. So, since U and V are both negative here, and both positive here, it looks like there is another region here in which U is going to be positive and V is negative. Now that's sort of obviously right, because if you stare at this expression, sending U to minus U and V to minus V doesn't change anything. If you take this expression, sending U to minus U and V to minus V doesn't change anything, and neither does it change anything here. So changing the signs of both U and V is going to send you to a region 4, which has got the same metric as region 1, but must be different, because over here U is positive and V is negative, whereas over here it's the other way around. Since this region has got the same metric as this one, you know that it represents another asymptotically flat region. So you discover that there is really 4 regions to the Schwarzschild space-time. There's the original thing that you had here. There is the interior of a black hole. There is this puzzling region, which is essentially the time reverse of this one. And then there's another region 4 that has precisely the same metric as this, but with big U and big V swapped round. This represents all there is to the Schwarzschild metric. It's usually called the Kruskal manifold. And it represents what is usually called the maximal continuation of the Schwarzschild metric. There isn't anything else. So you can sort of see what the situation is now. There is a black hole here. Because the entire situation is invariant under time reversal, there is something down here which is exactly the opposite. It's usually called a white hole, for the simple reason it's a time reverse of a black hole. If you sit in this region and you move along a causal curve, there really isn't much you can do. You will find yourself going in this direction, into region 1, or possibly into region 4, depending on your whim. If you try very hard, you could aim for this point here and go straight into there. But it will be a bit perverse. But region 3 is a region that you cannot stay in. Region 2 is a region you cannot escape from. If you are in region 3, the singularity is definitely in your past light cone, and you must have come from it. That is also a little bit puzzling and illustrates another of the rather puzzling features of general relativity. Namely, not only do you have singularities in the future, you have singularities in the past. You feel sort of comfortable about that when it was a Big Bang singularity, but you would feel desperately uncomfortable about this one. Well, I do. So that's the entirety of the Schwarzschild manifold. Now you might wonder what was going on here. We have a fairly clear idea of the geometry here and here, but there is this other asymptotic region. We can't communicate with it. If you are in region 1, there is no causal curve which intersects region 4. It's space-like separated. So that means that even if the Schwarzschild solution existed as a realistic description of something, you could be in this region and we would not know about this region. That may seem completely and utterly unphysical. How many people are doing cosmology course? So has the concept of eternal inflation been introduced yet? Okay, well exactly that kind of thing happens in eternal inflation, and it's, well again, leads to a large number of interesting enigmas. So for that reason, because it is enigmatic, it's rather interesting to try and look at the geometry of what happens between here and here. Obviously it's not causal, but it looks, were you to be some kind of super being, and you could investigate things at space-like separations, it looks like there might be a way of getting from here to here. Such things are usually called wormholes. This is a dull wormhole because it is space-like, but nevertheless is geometrically interesting. So to investigate the join between region 1 and region 4, the best thing to do is to look at a constant time surface. A constant time surface here you may as well take to be something that looks like that. So this is t equals probably 0, continued over to the other side. So I'm going to fix that, and I'm going to fix theta to be equal to pi by 2. So I'm just going to look at the r phi plane. The metric in the r phi plane, ds2 squared, is equal to dr squared over 1 minus 2m over r plus r squared d phi squared in region 1. Now perhaps it's worth our while drawing lines of constant r and t in this picture. I've already drawn one line of constant t. Here, in this region, they look something like this. And of course, t runs from minus infinity to plus infinity. If you reconstruct t from our formula for u and v, hardly surprisingly, it looks exactly the same. Looks something like that. In regions 2 and 3, it runs from minus infinity there to plus infinity there, and similarly, which looks like that. So of course t and r are swapped round in these two regions. So this works everywhere except at r equals 2m. Oh, wait a minute, we need to do constant r as well. Constant r lines look something like this. As r goes to 2m, you end up there. For r less than 2m, you go in this direction. And for r greater than 2m, in this region, it looks something like that. And again, you knew that because this one is isometric to that one, and this one is isometric to that one modulo time reversal. So this form of the metric is a nice space-like metric except near r equals 2m, and if you move along the surface of t equals 0, r starts out large here, decreases to r equals 2m at this point, and then increases again as you go out here. But there is a coordinate singularity at r equals 2m because this thing blows up. This thing is going to 0, so the whole coefficient blows up.
So what does the little 2 on the ds stand for?
It's just a two-dimensional space. And for r greater than 2m, of course, it has signature plus plus, indicating that it's completely space-like. So, the aim is to get rid of this singularity. So I'm going to define a new radial coordinate. I seem to have decided that r was equal to 2m cosh squared theta. Maybe theta is a bad letter to use because we put theta equal to pi by 2. Let's call it chi. That's pretty sensible as you go in this direction. Chi starts off as being very large. It decreases down to 0 here, and then continues along here being negative. So chi equals 0 is r equals 2m. Chi positive is in region 1. Chi negative is in region 4. And if you work out what this metric is, well, it's kind of nasty in chi coordinates. So I'm going to invent another new thing, rho 2m chi plus m sinh 2 chi. So as you can see, rho runs from minus infinity to plus infinity. As chi runs from minus infinity to plus infinity. Now that may look a little bit arbitrary to do two complicated coordinate transformations on top of each other, but you will see the point when you write out the metric in rho coordinates. You end up with d rho squared plus 4m squared cosh to the 4th chi d phi squared. So the point of this coordinate transformation was to turn this expression into just d rho squared on its own. And then of course you're going to get some function of rho here times d phi squared, but it's not easy to rewrite this thing as a function of rho except implicitly by that formula. So you've all come across examples of things like that, for example the cycloid in simple mechanics. So this represents the induced metric on a surface of t equals 0 as you go between region 1 and region 4. What does it look like? You know that for rho large and positive, everything looks as if it were flat space. Well, I can easily draw a flat plane. It looks something like this. For chi large, this is just looking like rho squared. So if it really were a plane everywhere, d rho squared plus rho squared d phi squared, then you would say if you were at a distance rho, then phi would correspond to some circle here, and the radius of the circle would just be 2m cosh chi. So rho equals constant surfaces have circumference two pi, because phi goes from 2 pi, times 2m cosh squared chi, where you want to think of this as being a function of rho. And we know that for rho large, this looks just like rho. So this basically is a measure of what's happening. Now, if this was really a plane and this coordinate rho went to 0, then of course these circles will get smaller and smaller and smaller until they collapse to a point here. Is that what happens here? Answer, no. If rho goes to 0, chi goes to 0, but if chi goes to 0, this thing tends to 4m squared. So as rho goes to 0, which is where r goes to 2m, instead of shrinking down to 0 size, what happens is it shrinks down to finite size. I can't draw that in R2 like this. You have to, so this picture is sort of an embedding picture in R3 of R2. So you have to sort of ask what happens. Well, what happens is, of course, that you are, as you go to rho equals 0, what you're essentially doing is constructing a tube of finite radius. So r rho is a coordinate which decreases in this direction. And then as you get to here, you find yourself, for rho decreasing towards 0, with something of constant size, namely 2m. So this is constant circumference of 2m times 2 pi as rho goes to 2m. Sorry, r goes to 2m, that's rho going to 0. But whatever this going on, rho, this surface is invariant, has a metric which is invariant under rho goes to minus rho. So if you go from there to there, the metric is the same. Send rho to minus rho, that's the same sending chi to minus chi, that's even, so the geometry is exactly the same. So that means you get a sort of mirror image of this. It looks something like this, where this tube sort of opens out into a second asymptotic region. So this is region 4, and this is region 1, and you discover this second asymptotic region, connected to the first by this thin tube. So there is a connection there is a tube which joins region 1 and region 4. So this tube is what is usually called the wormhole. Because it joins two perfectly normal regions. Well, as I say, this particular one is dull because it's space-like. So it's not much practical use, but it's obviously of considerable interest in principle. So, I think that's really all I want to say about the Schwarzschild metric. The Schwarzschild metric, in some sense, is the basic black hole metric. And apart from the fact that there are curvature singularities here and here, there are no singularities whatsoever, only coordinate singularities, and this illustrates a general fact about general relativity, that if you just pick some general coordinate system, you are likely to find singularities in the coordinates, but assuming you are sufficiently ingenious, you can get rid of the coordinate singularities. In the early history of general relativity, there was a great deal of confusion between coordinate singularities and general sort of irremovable singularities of this type, where curvature blows up, and they tended to get confused with each other. So I don't think it was really until about the early 1960s that the difference between the two different things was really fully understood. So if you want to look at old literature on general relativity, you will often discover that things are claimed to be singular when they're not. This is deeply confusing. So the whole history of the subject is littered with people who were deeply confused, Einstein being the obvious example. Einstein and Pauli even wrote a paper purporting to show that all solutions of Einstein's equations were singular, which isn't true. And they simply, well, plain got it wrong. So this is the Schwarzschild metric. You might ask yourself at this point whether there are any other metrics which contain black holes and whether they're different. Well, the answer is yes, there are a limited number of solutions, and there are only a limited number of solutions possible. So what I think I'm going to do next week is describe the other solutions. There are the Reissner-Nordstrom solutions, which are basically black holes that have electric charge. And then there are Kerr solutions, which are black holes that have rotation. And then there are black holes which have both rotation and charge, but they're not hugely interesting, so I will just tell you what those are. And it turns out that those are it. We have to do this in detail because they are different to what happens in the Schwarzschild metric in a dramatic way. What I will not do, however, is detailed calculations for many of these things because the Kerr metric is incredibly unpleasant. I will do it fairly explicitly for the Reissner-Nordstrom metrics because most of what happens in Kerr happens in the Reissner-Nordstrom solution as well. So I will be rather sketchy about Kerr and Kerr-Newman, but fairly thorough about Reissner-Nordstrom. We should probably stop there so that Professor Green can come in. Has everybody got the first example sheet?